First of all, I would like to thank very much Marco and Fabrizio for the opportunity to present in this web conference. Let me first spend a few words on why the cerebral cortex, among the various parts of the brain, is the most prominent and the most intensely studied. Ludwig Edinger, a German anatomist, was one of the first to rank mammals as the most intelligent animals in virtue of the cerebral cortex. This intellectual superiority remained almost undiscussed for a century. For example, by the American biologist Alfred Romer. This uniform superficial fold that replicate almost equally the organization in 6 layers and organized by an alternance of small vertical columns is held by many as the most sophisticated computational device in the universe. In fact, with the rise of comparative cognition, the intellectual superiority of animal with the cortex has weakened with the discovery of abilities previously thought to be exclusive to mammals in reptiles, birds, like the very clever parrots Alex. Moreover, the cortex did not pop it out from nothing. There are traces of cortex, especially in the pallium that holds the brain of all vertebrates. Also within mammals, there is a large variation in the complexity of the cortex. For example, the most characteristic cell, the pyramidal neuron, has an evolution of complexity in various mammals up to monkeys and humans. The cortex is also the part of the brain with the richest repertoire of cells. Okay, so this is just to introduce the speciality of the cerebral cortex. But what I'm going to discuss is a specific feature of the cortex that awaits an explanation. And it's what I call the paradox of the cortex, the clash between two properties. P1, the uniformity of the cortex all over its surface, and property 2, the fact that the cortex is the site of a great variety of functions. This has been a crucial issue for many neuroscientists. I collected here just a few citations, starting from David Marr, that wrote that the mammalian cerebral cortex can learn a wide variety of tasks, yet its structure is strikingly uniform. Kevin Martin, the apparent uniformity of the neocortex has given rise to the speculation that it is designed to perform the same basic operation. The tempting notion is that nature's laboratory has hit on a process that enabled it to use the same machinery for very different ends. I skip Häusler and Harrison Schaeffer very recently highlights almost the same kind of paradox. Broad similarity of all the cortex, not only between species but also between cortical areas, and the broad range of functions. Now, property 2 is not controversial. It's obvious that the cortex has a much wider range of function than any other part of the brain. On the other hand, the uniformity of the cortex has been the topic of a long debate. The first empirical assessment of the uniformity of the cortex is due to the seminal work of Rockel and others, who counted about 100 cells in section of 30 microns of cortex in motor, somatosensorial, frontal, parietal, temporal areas, and across animals such as mice, cats, monkeys, and humans. However, their observations have been the subject of a strong debate for over 30 years. For example, Susanna Herculano-Hausel titled her work "The Basic Non-Uniformity of the Cerebral Cortex," and the main criticism is that Rockel had used a flawed methodology. However, recently, Carlo and Stevens replicated the same measures of Rockel, but with modern equipment, and they found almost the same results. In addition, Karbowski, but also others, found a number of additional parameters that are remarkably constant across species and across regions, like synaptic density, ratio excitonatory to inhibitory synapses. So we may conclude that at least the cortex is much more uniform than the rest of the brain, and enough uniform to support the paradox of the cortex. Now, in reviewing what has been proposed so far for explaining how the cortex works, it is useful to track what I think are the roots of what I like to call the electrical epistemology in neuroscience. And this is a very special event that makes electrical engineering so popular when in 1858 the transoceanic cable was start to work with the message sent by Queen Victoria to the President of the United States, Buchanan. And William Thomson, later Lord Kelvin, gave a fundamental contribution to this epic project by deriving the equation of the electrical transmission in the cable. And thanks to this theoretical advance, it was possible to successfully build a cable after 3 big failures of previous attempts. This equation was derived by Kelvin from a similar equation of the thermal diffusion in solids. Now, this equation has been fundamental in neuroscience for a very different sort of cable, in particular axons and dendrites and neurons, for which David Goldman made the first attempt to write a mathematical equation that was just based on the gradients of ion concentration and membrane permeabilities. But it was Wilfried Roll who borrowed the equation of Kelvin adapted for neurons. This is the basic equation of Wilfried Roll, and this is the cable equation of Kelvin. You can see that are exactly the same equation. There is a second fundamental contribution from electrical engineering to neuroscience, with the shift in the theoretical treatment of electricity by Gustav Kirchhoff from the field perspective, electrical and magnetic field, that of Maxwell, to the idea of circuits made of discrete ideal components and perfect conductors. In addition, Oliver Heaviside made a step forward introducing a complete taxonomy of the ideal components that can take place in the circuital abstraction. At about the end of the 18th century, there were the use of drawing sort of circuits, but were just pictorial representation where each component had a physical resemblance to the component itself, while in the electrical circuitry abstraction, components bear no resemblance with their physical appearance. There was actually a very strong interaction between electrical and electronic engineering at the beginning and in the first half of the last century and neuroscience. Today, every student of electronic engineering come to learn the trigger of Schmidt, which is one of the basic circuits, but few students know that Otto Schmidt actually conceived these circuits for just the purpose of simulating the electrical behavior of neuron membranes. And 2 decades later, Leon Harmon invented the neuromime, which is a similar circuit but much more complete, thanks to transistors, for the study of at least some phenomena in the electrical behavior of neurons. This thread of neuromorphic circuits come to a top end with Misha Mahawald, who in 1994 succeeded in exploiting VLSI, very large-scale integration chips, analog chips, in reproducing some aspect of retinal neural cells. And she was noted by Douglas and Martin, who will be the fundamental proposer of cortical circuits. And in the words of Douglas and Martin, the advantages of using such a method, that is, the implementation in analog very large-scale integration circuits of simulated neuron, the advantages of using such a method for exploring the functions of the canonical microcircuits of neocortex are immense. They say that we began to realize that biological computation is very different from digital computation, and that the neocortex may indeed be the source of yet undiscovered strategies of processing. So they recruited Misha Mauwald in Oxford first, then they moved together in establishing the new Institute of Neuroscience in Zurich. But sadly, a few years later, Misha Mauwald died, and this project never started. And Douglas and Martin then moved to just a theoretical assessment of sort of electrical circuits of the cortex. There has been a sort of precursor due to David Marr, who in this very difficult paper, long paper, tried to develop a full mathematics of how the cortex works from the point of view electrical connection of a series of components corresponding to neural cells in the cortex. This was a very ambitious project, totally speculative, that in fact did not find corresponded with empirical data, and Marr himself later on shifted drastically his view. So the real first circuit of the cortex was suggested by Gordon Sheffer. He proposed that the specific information processing in the cortex is related with the cooperation of superficial and deep pyramidal neurons together with feed-forward inhibitory connection of superficial neurons, SI, and feedback connection through a basket cell. He drew these two versions very similar of the same circuits. And Sheffer claimed that certain modes of information processing are possible within a cortical type of organization that are not possible with other non-cortical types. But the most famous circuit of the cortex is due to Douglas and Martin when, while in Oxford at the Anatomical Neuropharmacological Unit, and their circuit is even a bit simpler than that of Sheffer, but still based on two pyramidal neurons, one deep and one superficial, cooperating together, and with just one inhibitory cells. Here in red are the inhibitory connection, and the excitatory connection in blue. They boldly claim that now there are scenes from experimental theoretical work on the neocortex that we are on the threshold of a revolution in which the hegemony of the single neuron will be replaced by much more circuit-oriented concepts. And this is the highest interpretation of the electrical epistemology in neuroscience. This is just the beginning of a long road along which the derivation of a solution of Raoult's equation for each neurons become more and more sophisticated with simulator like Genesis and Neuron. But the essence was still the same, applying the cable equation at small groups of interacting neurons up to what is now the highest achievement due to Henry Markram, who simulated 3 square millimeters of the somatosensory cortex of the mouse with 30,000 neurons and millions of synapses using one of the most powerful computer in the world, the IBM Blue Gene. And his model is exactly a replication in a larger scale of the canonical circuit of Douglas and Martin. Now, the question is, are circuital models of the cortex mechanistic in the sense given by, for example, Karl Krever in his book? And since circuits have a corresponding mathematical description of the components and their interaction, is this computation compliant, for example, with the mechanistic account of physical computation given by Gualtiero Piccinini? We can apply what is called the 3M constraint proposed by Kaplan and Krever to attempt an answer. In these constraints, for example, it is necessary that the variables in the model correspond to identifiable components, activities, organizational features in the target mechanism. Now, if we take the lower part of the canonical circuit of Douglas and Martin, this is made by electrical components in a Raoult-style compartment description of a neuron. Well, there is some sort of correspondence. For example, the capacitors roughly correspond to properties of the membrane of the neuron. The electrical generator bear correspondence with ion channels. And, B, without perhaps mathematical dependency posited among variables in the model, correspond to causal relations among the components. Yes, they do. The relations described in the differential equation of the electrical behavior to correspond at least to some aspect of the electrical behavior in one single neuron. So this group of parts and relation correspond to just one single cell. We can move to the higher level of the full circuits of Douglas and Martin, and we still can find some correspondence between variables in the model and different cells in the cortex. So the answer can be yes, at least in part. There are several aspects that deserve more discussion. For example, here one elements do not correspond actually to one cells, but it's rather the cooperative behavior of a population of cells. So there are several problems. It's not a perfect mechanistic model. For sure, canonical circuits are capable of simulating several phenomena, like the ability to amplify very small signals, the ability to sustain activity due to a signal after the signal ends in time, the ability to have responses selectivity to patterns of signal and inhibited by other patterns. In this work, Douglas and Martin apply the canonical model to aspects of visual processing, and with two canonical circuits together, they were able to have strong responses in case of a pattern that come in time to the left circuit first and then to the right, and to inhibit the response when the temporal ordering is the opposite. And if we agree that canonical circuits are mechanistic, we can also claim that the models have explained this sort of phenomena. But a big failure of the model is in giving an explanation of the paradox of the cortex that I wrote here again, the clash between uniformity and variety of function. All proponents of circuits were well aware of the problem and gave some answer. Shepherd the answer of Shepherd is that the basic circuit can be expanded with sub-circuits for specific functions. One begins with the canonical circuits and introduces the particular adaptation, elaboration that underlines its unique properties. So it's just a matter to add sort of sub-circuits. Well, the difference is the proposal of Martin. The only thing that would distinguish, for example, auditory cortex from motor cortex is that it has different sources of input and sends its output to different targets. Well, we can try to rewrite property 2 with the two different answers. Property 2 with Shepherd's proposal is the variety of function in the cortex can be accounted by the integration of the canonical circuits with subcircuits. By Douglas and Martin, the variety of function can be accounted by the different inputs and outputs. But Douglas and Martin recognized that this answer was far too simplistic. They wrote, we should certainly not expect the present course of experimental and theoretical work to provide us with an early answer as to how neurons become, for example, orientation selective or direction selective. Although the solution of any of these problems would be very impressive given the trail of failed attempts, it is also not self-evident that we would thereby arrive at any general rules about the operation of the cortical circuits. And the big piece that is missing, in my opinion, is plasticity. Plasticity is what drives, in general, changes in the brain. Plasticity is a very ambiguous term, and it can be defined according to very different criteria. I just try to summarize in this slide few criteria. According to which is the domain of research, plasticity is studied concerning the organization of the nervous system after injuries. This is the main concern of plasticity for example, clinical neuroscience, or in research about the ontogeny of the brain, or in everyday memory formation. A very influential work of Kolb and Gibb draw a taxonomy depending on the role of experience, expectant, independent, and dependent. So far, concerning plasticity in the entire brain, but cortical plasticity is special, and Bonomano and Merzenich wrote a seminal paper about specifically the plasticity in the cortex, proposing their own taxonomy that is actually depending on the type of external manipulation that give rise to plasticity. I, in work with Marco Mazzone, proposed a criteria based on the grain of circuitry, synaptic plasticity when involved just two neurons, intracortical plasticity when it involves just a single cortical map, and intercortical map plasticity when changes happen on a scale of more than one cortical area. There is a huge evidence of plasticity in the cortex, but I would like to mention just one of the most striking, done by the group led by Brigham Kasour at MIT, with the rewiring of the auditory cortex, so to get visual inputs at birth time in ferrets. And what happens after development is that the rewired auditory cortex has a map of orientation selectivity to visual inputs similar to that of the primary visual cortex. And this profound different behavior from the natural behavior of the auditory cortex is established thanks to a broad reorganization of connections. Looking at connection, this is the long horizontal connection from a central neuron, this one. In normal, A1 is very local, and is elongated anterior-posteriorly, while in the visual cortex is much more patchy, as is elongated mediolaterally. The same happened in the rewired A1. is very interesting what suggests as a putative mechanism for such a striking plasticity. We suggest that a response feature that depends specifically on the two-dimensional nature of visual input indicates a form of adaptive self-organization in cortex. The mechanism behind such organization might generally involve spatiotemporal coactivation in subsets of the visual input, along with lateral inhibition, and so on. There has been, in fact, a thread of research within neuroscience that try to describe self-organization in the cortex, borrowing clearly from the mathematics of the self-organizing systems in physics, especially the mathematics as laid down by Hermann Haken in synergetics. And there are clearly phenomena of self-organization in the cortex, like orientation selectivity or occurrence dominance. The point is that there has been, unfortunately, no intersection, no cross-fertilization between this field and the mainstream circuital-based research. There are just few examples. Christopher Mansburg was the first one to try to write equations for the development of ocular dominance pattern by using the mathematics of self-organization. There is a more recent neurocomputational frameworks called LISSOM, Laterally Interconnected Synergetically Self-Organizing Map, developed by Mikuláinen and especially James Bettner, aimed specifically to simulate the self-organization through plasticity of a cortical map, including excitatory and inhibitory long horizontal connection with equations that derive from the cortical plasticity.
Alessio, please move to the conclusion. We're running out of time, sorry.
Yes. In my opinion, without an interaction between developmental and circuital models, there is little hope to progress in explaining the main paradox of the cortex. And today, we don't see efforts towards this integration. Thank you for your attention.